So this brings us to the end of chapter 4, which is integration by substitution, which I found that you'll either really love and think it's kind of cool to be able to find those substitution patterns, or you may hate. Hopefully you're in the first camp. So here's our objectives. We're going to look at pattern recognition, we're going to look at change of variables, we're going to use change of variables with definite and indefinite integrals, and then evaluate a definite integral involving an even or odd function. So before we get going with integration, I want to just remind you how we used the chain rule before with derivatives. And when we did this before, what we were looking at is, and I'm going to talk about it this way, we can look at the functions f of g of x. Remember, this was a composition, f of g of x. And that's what I've shown you here, but I want to work through it using u substitution because that's the way I'm going to show you all of the remaining examples. So if I wanted to take the derivative with respect to x of 3x plus 2 quantity squared, I could write this instead as u squared, where I let u be equal to 3x plus 2. So now if I find the derivative of u squared, that's telling me that it's just 2u to the first times u prime, the derivative of u. So the derivative of u is 3. So this would be 2 times u, which is 3x plus 2, times u prime, which is 3, which leaves me with 6 times the quantity, 3x plus 2, which I could distribute if I want. But it gives me the same answer if I look at it in terms of functions as well. That way just doesn't track with me. I just like the u substitution better. Now, why is that important? Because now we want to go in the opposite direction. So if I'm able, and you're going to see me use u all of the time on this, so I'm not going to be using f of x and g of x and l of x, I mean whatever, I'm using u. So what I'm going to do is look for a pattern, and that pattern is essentially going to be the chain rule pattern, is that pattern recognition that I'm going to be looking for. So if my original function that I'm going to integrate contains the composition of a function, which means I can use u substitution inside, then that's going to help me to very easily find the integral. So that won't make sense until we actually do some, so let's do some so it makes sense to you. So let's take a look at these together, and I've purposely not shown you the solutions because I want to really show you the process that I go through when I do this. So when I do this, I take a look at my function, and I'm saying, what I have is something being taken to the 4th power, and then I've got this extra something over here. So we're not going to worry about the extra right now. I'm just going to take this and rewrite it. So I'm going to say, let's let u be x squared plus 1 to the 4th. Nope, just kidding. Let's just make it be x squared plus 1. We'll do the 4th part in a little bit. So that's just this part here in the middle. And I also want to find u prime, which I'm actually going to call du, because it's the derivative of u. So du would be 2x. What I want to do now is I want to rewrite this guy using u's instead of x's. So this guy turns into u to the 4th, and then this guy is actually du. So I'm not deriving or integrating with respect to x, I'm integrating with respect to u, so it makes sense, and if it makes you feel better, you can say this is 2x dx, because that will help you get rid of that dx in your mind. But essentially I'm just replacing things with what I've assigned to be u. So why is that helpful? Because now I can integrate this. How do I integrate something to the 4th power? Remember, I take it to 1 greater power and divide. So now I've got u to the 5th divided by 5, and guess what? Plus c. So question is, why do I use plus c? I haven't had to do it for the last several lessons. Well, the last several lessons have dealt with definite integrals. And I don't have that right now. I have an indefinite integral. And remember, we always use c with indefinite. From here, I'm just going to plug the u back in. So this is x squared plus 1 to the 5th divided by 5 plus c. And that's my final answer. Let's look at another one. Again, I'm going to take this function and say that that's u. So u is x cubed plus 1, which means u prime, or du, is equal to 3x squared dx. So now let's rewrite this function using all of this business up here. This guy turns into u to the 1/2 because it's the square root of what I assigned to be u. 3x squared dx gets replaced by du. So I'm integrating u to the 1/2 du. That means now I'm taking u to the 3/2 divided by 3/2. So that's exactly what I have here. U to the 3/2 divided by 3/2 plus c. Obviously that's a hot mess, so I'm going to turn this into 2/3 u to the 3/2 plus c. And that means now replace the u back in there. So 2/3 u is x cubed plus 1 to the 3/2 plus c. And I can leave it just like that. You don't need to write it as the square root of the quantity to the 3rd power, etc. Leave it just like that is perfect. I'm really not going to go over this one. This is basically formalizing exactly what we've just been doing. If you're going to take the antiderivative of a function, you need to make sure the derivative of the u substitution part of it is in there. So that's why we use that pattern recognition, is because we know that we're getting using that chain rule, getting the derivative of whatever that u function is. So let's do a few more practice. Again, you should be able to do this yourself now. So this is using that pattern, which is essentially the same pattern with u and du is what we're looking for. So just try these questions. When you're done, press play to see how you did. So let's take a look. Again, I would call u to be x squared plus 1, which would make u prime, or du, to be 2x dx. And that worked out really well because now I have the integral of u squared, and then 2x dx is now du because I'm integrating with respect to u. That's going to be u to the 3rd over 3 plus c, because we always use plus c for an indefinite integral. Now I'm going to put the u back in there, so I get x squared plus 1 to the 3rd divided by 3 plus c, final answer. Now let's take a look at our next one. If you ever get confused as to what pattern or what your u should be, some people might say, well, let's let u be the cosine of 5x. Well, if I did that, what's u prime going to be? It's going to be another trig function, right? And I don't have another trig function already in my integral, so don't use that. So I'm going to let u be 5x, which means du is 5 dx. So when I rewrite this integral, it's the cosine of u du. And so what is the integral of the cosine? Well, that's sine of u plus c, which means sine of 5x plus c. So I want to go through a question with you that is pattern recognition but doesn't quite fit as much as we'd like it to, and here's how it works. If I were going to work through this, I would say that u, let's try a better handwriting, u is x squared plus 1 and du is 2x dx. So when I integrate this and I start to substitute, this guy obviously turns into u squared very easily, but I have a problem because this needs to be 2x dx and it's just 1x dx. So how do I rectify that problem? Well, let's just take it times 2. But is that illegal? Can I just randomly take it times 2? No, I can't. But I can take it times 1 and that would be 2 and also a half. So I can put a 2 on the inside and a 1/2 on the outside, and what happens now on the inside is I have 2x dx, which is what I wanted, so now I have du, and on the outside I just have to add that 1/2. Now from here I'm just going to work through it like I normally would. What is the integral? I'm going to keep the 1/2 on the outside. What's the integral of u squared? U cubed divided by 3 plus c. And I don't have to worry about taking the 1/2 times c because it's some random constant that I don't know. So it's plus c or plus 1/2 c, it's just c. This I'm going to reduce, so I get 1/6 u cubed plus c. And then of course I just want to replace u with x squared plus 1 cubed plus c. All done.